So as you are working with the AC theory, you are going to see that in major calculations, you are going to have an application where the complex numbers are needed. Remember, even if you are to just write in complex notation, maybe you are presenting a resistance and an inductance. We have got this notation whereby we are writing R is R plus JXL. Maybe we are talking about a capacitive circuit, which is consisting of a resistor and a capacitor, where we have got R, which is Z is equal to R minus JXC. What is this that we are representing? This is complex notation. Whenever we have got this J that we are saying, that is a presentation of the complex numbers. So we need to understand these complex numbers as we are going to work with the complex numbers notation. Maybe we are given a format of a number and an angle like this. This is given as your impedance, whatever that you have. It is a part of the complex numbers that you are presenting. So as we do understand from our N4, if you had mathematics N4, you worked with the complex numbers, that part is still the same that we are going to refer to. Remember, in our complex notation, we've got two major formats or the ways that we can present the complex numbers. We have got the rectangular form, okay, and also we have got the polar form. So these are the major formats that we are going to have, the rectangular form and the polar form. So in a rectangular form, a complex number Z can be given in the form of A plus or minus JB like this. Okay. In a polar form, we are going to have this in the form of R angle of theta like this. So that is the presentation of the polar form, where we are going to have now only two things to consider: resultant and the magnitude that you have, which is the magnitude, and the resultant, which is whenever you're talking of the magnitude, presenting the resultant that you are given there, which is this R that you're having, and the theta being the argument, which is the angle that is affecting, is called the argument there. So this is a notation, guys, a presentation, just like our mathematical presentation. So this being our rectangular form, what is it that we are having here? We have got the A, which is representing the real part of the complex number. That is the real part of our complex number in that case. Then we move on to the imaginary part, which is this part that is representing the B with the sign that you're going to have there. So the B is part of the imaginary part, which is this part that is having a J. So if you were to take this into consideration, you're going to see that we can actually present this complex notation in a rectangular form on what is referred to as an Argand diagram, where we have got the real axis and we have got the imaginary axis on this other side. So the imaginary axis is the one that carries the J. So this is represented with a J. So meaning to say, if you are given a complex notation in rectangular form, it depends with what you are given in this case. Is this a positive or a negative? So considering that these two are positive, let's say A and B are positive, we are going to see A along the real axis and B along the imaginary axis. But they will meet at a certain point, as we are to consider the distance this side, which is A, and the distance this side. They will meet at a certain point as you are going up, as you are going this side, they will meet at a certain point. So the indication of this complex number can be presented in this format. So what is important that we are seeing here, it is that this is just a point where these two meets, the A and the B. So considering that these are numbers now, okay, we know these guys from our N formats. Let's say we have got 4 plus J3 like this. It means we are going to have in the real axis and the imaginary axis where we've got our J like this. The 4 is positive. We are going to have it this side. 4 positive. The part of the imaginary being positive also maybe somewhere there. Okay. So the 4 going up, the 3 going this side. As you can see, these two, they will meet at a certain point here. Where they meet, you mark a point. That point, it indicates where these two meet. The distance that we have taken 4 units in the real and 3 units in the imaginary axis. That is the condition. So you can actually have it this way. So that is, if you understand this, you can also understand the presentation now when it is given in form of a capacitive circuit or it's an inductive circuit that you're given. You can even present it. Remember, we talk of the phasor diagram. The presentation of that phasor diagram is the same way that you're going to present even here. So that is the major part. All right. So like I said, having a rectangular form, it's a format that you have. It's a format that which can also be converted to the polar form. So how can we convert from this rectangular form to the polar form? That is where you are finding R in this case, where we can simply consider this R in this case is this part. Remember, this is A, the whole of this distance, and the distance going up here is the same as this B. So if you are to consider to find this R, we're simply going to apply the Pythagoras theorem. This is a right angle triangle, guys. Remember, R squared is equal to A squared plus B squared. So to find R is simply going to introduce the square root. So that is the square root of A squared plus B squared. So in this case, we are going to obtain this formula for finding R. Then we can also determine the theta, which is the angle that will be inside here. So considering that this side where B is, according to the theta from our trigonometrical ratios, this is opposite. A is representing the adjacent. Which ratio do we use with opposite and adjacent there? That is from our SOHCAHTOA concept, opposite adjacent from tan. So meaning to say that theta, we can determine this from tan. Okay, so it's going to be arctan. So theta is going to be arctan of what? Opposite over adjacent, which is opposite, that is B, over adjacent, which is A. So you can have a formula like that, where sometimes now further adjustments need to be taken into consideration. But if you're talking of the simplification, just use it like that. We have the formulas that we can actually apply or use in our simplification. So if I've got anything of this nature, in place of this R here, it means we can have it like this. We can just have it in short. All right. So we can conclude that this Z can also be given as, in place of this R, this one, what are you going to use? You're going to use this. So you're going to use what is representing our R. Our R is represented by the square root of A squared plus B squared. And what is representing the angle theta? The angle theta is represented by what? By arctan B over A. So you can actually use it that way. In short, we can see that this presentation that we are seeing is exactly the same as this. We can write this, or maybe you can just calculate this aside. You calculate this aside, then you substitute whatever that you're going to have there. It's a simplification that you're having, converting from one form to another. You must know the conversion from one form, because in calculations, remember, the rectangular form, there is where it is important to use the rectangular form. I'm going to talk about that. Let me quickly have an example here. Let's say we are given Z, which is equal to 3 plus J4 like this. And we want to convert this to the polar form. This is rectangular form, as you can see. So we can write this same Z in polar form. where we can calculate our r using this formula, then our theta using this formula, or you can simply use this formula direct as it is. Remember, this is your A, this is your B. So we can simply calculate this as the square root of, from this formula, square root of A squared plus B squared. So it is the square root of 3 squared plus 4 squared. This is our R. Then what are we going to have from this? The angle now, theta. So the angle theta is arctan. So this is arctan B over A. So that is 4 over 3, just like that. So we can simplify direct like that. We can do this. So this is what we are going to have. I'm just going to quickly show this here. That is the square root of 3 squared plus 4 squared, like this. And that is going to be 5. So as you can see, this is going to be 5. Then the angle now, that is arctan. So this is, make sure that your calculator is in degrees. So that is shift tan. Remember, we need arctan. So it's going to be shift tan 4 over 3. That is 4 over 3, like this. So that is, we now have got the angle, which is 53,13. All right. So that is going to be 53,13 degrees. So if this was an impedance that you are given, Z is equal to this in ohms, meaning to say we've got our same Z in ohms again, but this being in polar form. So why is it important that we need to know these two formats and the conversion part? It is in calculations. Whenever you're calculating, you see the importance of each. So you can convert from rectangular form to the polar form. In the vice versa, you can do the same thing. You can have a conversion from polar form. You can have a conversion which is taken from polar form to Cartesian form, which is the rectangular form, right? To the rectangular form. We can have a conversion of this. Remember, in polar form, we were having our Z in the form of our angle of theta like this. This can be written, this part can be written in the rectangular form. This A here representing r cos theta. So it's r cos theta plus the imaginary party is going to be rj sine theta. So for us not to have confusion here, I'm just going to write this as j like this. I'm going to have this as j r sine theta so that we can properly see that this is representing the same A that we had before. This is representing the same B that we had before. So meaning to say the r cos theta that we are seeing here is the real part. And the r sine theta is the imaginary part. There we are having the imaginary part. That is the condition there. We're having the imaginary part, right? That's an A there. And there we've got the real part. That it is now converted to the rectangular form, because rectangular form, we must see the real and the imaginary. Once we see this, we are in rectangular form. So meaning to say we can convert a number which is from polar form. Maybe we are given our Z, which is 5 angle of 30 degrees like this. This is in polar form. And we want to convert this to rectangular form. So how are we going to write it in a rectangular form? We are going to have this as Z is equal to r cos theta, where this is our r and this is our theta. So that's r cos theta, which is 5 cos of 30 degrees, the angle that you're given there, plus j, representing now the imaginary part. So it's going to be r sine theta, that is 5 sine 30 degrees. As we can simplify this to obtain this in the rectangular format. That is, the conversion is important. So that's 5 cos of 30, and that is going to be 4,33. All right, you can also do this, guys. Shift, then set up, then fix your calculator to 3 decimal place. That's 4,330. So that's 4,330 there. Then 5 sine 30 degrees, which is simply 2,5 there. 5 sine 30. That is going to be 2,5. So that's we're going to have plus j 2,500 like that. So that's we can write this in a format that we understand depending with the calculations. So the question is, where exactly is it important for us to apply the rectangular form, and where exactly is it important for us to use the polar form? All right. As long you are working with addition and subtraction, you're going to see that the rectangular form is important to use or to apply whenever you are working with addition and subtraction. As long you are working with addition and subtraction, use the rectangular form, meaning to say if numbers are in polar form, you have to convert them. You are working with the circuit, but you are given values which are in polar form and you need to add. You have to convert them to rectangular form so that you'll be able to add or subtract. The polar form is best for the multiplication and division. Okay, so whenever we are referring to the multiplication and division, use the numbers in polar form. Why is that so? All right, let's get ready. Let's get this into consideration. Remember that in rectangular form, like I said, it is the easier part for us to perform addition and subtraction. We can simply add two complex numbers given Z1 is equal to A1 plus JB1 like this. And we're also given Z2, which is equal to A2 plus JB2 like this. We can add, we can subtract these two by simply adding or subtracting the real terms together, the imaginary terms together. So meaning to say, if I was to find Z1 plus Z2, I simply add these together, the real part together, A1 plus A2 plus J, the part of the imaginary on its own, which is B1 plus B2. So it's easier for us to perform addition. So meaning to say, if it was a minus, we're going to have a minus here. We're going to subtract. We are going to have the difference there. So simply subtract whatever that you're given. It's easier for us to perform this addition. You are given two complex numbers that you are adding. Let's say you are given 3 plus J7 like this in a bracket plus 4 minus J2 like this. It's addition. You can simply expand this. There's a 1 here, there's a 1. So you simply expand 1, which is 3 plus 1 and J7. That is J7, 1 and 4, which is 4. You're expanding the brackets. That is 1 times 4, which is 4. 1 times minus J2, which is minus J2. So what are you going to do? You're going to take the real terms together. So adding and subtracting, it's real terms on their own. So you add, which is going to be 7. The imaginary on their own. So meaning to say, this is going to be 7 minus 2. Remember, there's a minus there. So it's 7 minus 2, which is going to be a 5. So that's J5. This is a normal simplification that you are used to. So addition and subtraction, consider that you work your numbers in rectangular form. They'll be easier. meaning to say, if they are in polar form, you must convert first to rectangular form. In polar form, as we saw, that it is easier for us to have a division in polar form. Why? If you are given, let's consider Z1, which is R1, angle theta 1, and you're also given Z2, which is R2, angle theta 2, like this. We can simply divide Z1 over Z2 in which way? Remember division. All right, let's take our Z1 as it is. That's R1, theta 1. Our Z2, that's R2, theta 2, like this. So it follows that under division, remember in your complex numbers N4, you divide the numbers on their own, meaning to say you're going to divide R1 and R2, these two on their own. What about the angles? You subtract. So meaning to say this is going to be theta 1 minus theta 2. You subtract. That's for a division. If it was a multiplication whereby we've got Z1 multiplied to Z2, it was going to be the product of these two. Z1, which is R1 theta 1, multiplied to Z2, which is R2 theta 2. So what is going to be the resultant? You multiply the numbers which are outside of these angles. The resultants that you have R1 and R2. So it's going to be R1 times R2. What about the angles, the theta 1 and theta 2? You add them. Theta 1 plus theta 2. So as you can see, it's easier for us to divide or multiply in polar form. Then we can do the conversions later on. Thereafter, we can do the conversions to say, how are we going to convert now to the rectangular form? First part is the simplification before the conversion. So like I said, you need to understand this in your simplification. So I'm just gonna have one question, which is just a little bit to consider in our revisions. Also, just one or two questions. Remember, in our simplifications, the way that you simplify also will differ, like the way that you understand. Like, let's say, for an example, you are given to find the value of or to evaluate 3 plus J4, everything over 1 minus J2. Okay, plus 3 minus J8. Remember when you're doing your mathematics N-form, you had a condition whereby whenever you've got something of this nature, you can simply think of the complex conjugate. Okay, when you talk of the denominator, the way we need to get rid of what? The denominator to be a real term. Remember that. You can do that. Okay, so I'm just going to use that basic of your N-form maths, where you can also apply that. 3 plus J4 over 1 minus J2, like this, plus 3 minus J8. Remember, we need to get rid of the denominator to be a real term. So we need to multiply by the complex conjugate. So let me just separate a little bit here. So we need to multiply by the complex conjugate of the denominator, where we introduce a negative on the imaginary part. So if I introduce a negative, it will be a positive. That's 1 plus J2 over 1 plus J2. Remember your N4. So you're going to expand the brackets in this case, because this is now a bracket where you're multiplying this to this bracket. Okay, let's multiply and see what we're going to have. 3 times 1, which is 3. 3 times J2, which is J6. You move on to J4, J4 and 1. That was going to be J4. J4 and J2, this was going to be J squared times 4 times 2, which is 8. So it's J squared 8. The same thing in the denominator, but also that we do understand from our mathematics that a complex number times its complex conjugate can be simplified direct. Okay, what am I trying to say? A minus JB multiplied to A plus JB like this is simply equal to A squared plus B squared. A complex number to its conjugate, meaning to say if this is a plus and this is a minus, you're simply going to have A squared plus B squared. A difference of two squares of complex numbers adds. Take note. A difference of two squares, like what we do understand, here it will be adding. So it's just A squared plus B squared, where A and B are simply the numbers, the 1 and 2 here. So it's simply going to have 1 squared plus 2 squared. Yes, you can expand your brackets. I'm not saying it's wrong, but guys, just try also to minimize your work. So all this, we are trying to have this in a simplified way, and we can add this to 3 minus J8, which is remaining there. So we've got 3 minus J8. All right, let's simplify our complex number here, which is, remember, J squared from our maths is minus 1. So wherever we've got a J squared there, we have got a negative 1. So I'm going to remove this J squared with a negative. So meaning to say it will be 3 minus 8, which is minus 5. The J6 and the J4, remember these can be added. Simply add 4 plus 6, which is 10. So that's J10. Everything over 1 squared plus 2 squared, which is a 5. Plus 3 minus J8. So as we can see, we can have this in a simplified way where we can divide each term that we are given here by a 5. This here is simply as minus 5 over 5 plus J10 over 5 like this. So this and this is going to cancel. That's a negative 1. 5 into 10, that's a 2. So that's J2 plus 3 minus J8. That's where we are. Now we can see that, oh, there are real terms there. We can collect the real terms together. Minus 1 plus 3, which is 2. The part of the imaginary, J2, and the minus J8. So you're subtracting there. 2 minus 8, which is minus 6. So it's going to be minus J6. So the simplification there, it was a procedure where you are to get rid of the denominator in this case. This is from our end formats. We understand this. Okay. What if we try and have this way? Because we do understand that division is best to be applied in polar form. Because there's a division, and I do not want to apply the complex conjugate because this is not in maths, guys. This is industrial electronics. We are not in mathematics. Unless you are a mathematical person, then use this way. You are used to that. How can I just save this in short? Remember what I said, division is best to be applied in polar form. So we can simply have this in polar form. So meaning to say this was going to be in polar form. Remember, this is our A, this is our B. And I said in polar form, guys, instead we can just have our Z in place of R angle of theta. Remember what R represents. It represents the square root of A squared plus B squared. Remember what theta represents. It represents arctan of B over A. We talked about that from our formula. So meaning to say, I can just indicate this direct. This R here, which is represented by the square root of A squared plus B squared. So that's 3 squared plus 4 squared. Okay, then we have got the angle, which is arctan, the angle B over A, that's 4 over 3. This is what you're going to have. Everything over what? We do the same thing. This is our A, this is our B. So we're going to have the square root of A squared plus B squared. That's 1 squared plus B squared, which is minus 2. So that's negative 2 squared, which you can just write as 2. No problem. The angle now, theta, is arctan. So this is arctan B over A, which is minus 2 over 1. But there is this part which is to be added, and we do understand that addition is best to be performed in what? in rectangular form. So we're going to leave it like that. Here we want to divide. So that's why we are converting to the polar form. All right. So we are going to simplify this. 3 squared plus this under the square root is going to be 5 arctan. The square root, I think we talked about this, guys. We simplified this before. Anyways, let us just sim. That's arctan 4 over 3. Shift tan 4 over 3. All right, let's see what you're going to have there. That's 53.18. So because here we are using rounded off values, it is not going to be 53.13, sorry. It's not going to be exactly the same answer as what we got before because we are working with rounded off values. All right. Then we do the same thing on this square root of 1 squared plus negative 2 squared. So it's going to be square root of 1 squared plus negative 2. It just says 2 squared, that one. That is square root of 5. Then the angle, it's arctan negative 2 over 1. So it's simply arctan negative 2. Okay, standing here, negative 2. All right, you see now these softwares, guys, they just tend to misbehave. That's negative 63,4, negative 63,435. All right, so that's we have got something like this. And this part is the remaining 8. All right, so this is where we are. Remember the purpose of having this division. It is because the simplification is easier for a division. We are simply going to divide these numbers. Remember what I said in for the division? The angles you subtract. That is what we know under division. So it is up to you guys. As you can see, there are a lot of steps, this and that. But if you understand that, it is going to be easier. So this part, you are going to divide. Okay, so you divide this part, 5 divided by the square root of 5. What are you going to have? Let us just see here. 5 over the square root of 5. Okay. So, sorry, that is the square root of 5. In this case, which is same as 2,236. So we have got square root of 5. Okay. Into the angles. Remember what are you going to do with the angles? You subtract. So meaning to say this is going to be given as 53.13 minus, you subtract this angle which has got a negative. So there's a negative there, 63,435, like that. So this is going to be 116,565, something like that. So it's going to be 116, sorry for that, 116,565. Is that so, guys? That's 565 there. Sorry for this. Decrease. And what about this? It's still in rectangular form. So we've got plus 3 minus J8. This is where we are. All right. So at this stage now, you can see that these two are to be added. And this is in polar form, which cannot be added to something in rectangular form. So from our simplification, I said it is best for us to perform addition in a rectangular form. So meaning to say, you will be forced to convert this to rectangular form, back to rectangular form for addition. Remember, how do you convert to rectangular form if you are given r theta? That is equal to r cos theta plus j r sin theta. So you're going to apply that. That is r cos theta. So it's going to be the square root of 5 cos theta, 116,565. So this is actually representing the real part. Okay? Plus the imaginary part, which is going to be j sine. So we are going to have the sine of the same thing, right? So there's a r there. So our r is square root of 5. So that's r sine theta, which is 116,565. So this is representing the imaginary part. So that's we've got plus 3 minus j8. Okay, which is this part that we had before. So meaning to say we can simply add these two because they are real parts. This one, guys, the part of the real, it means we do not have a j there. We do not have a j. So it can be added to 3 direct. You can simply use your calculator, they add. It can be added like that. So this is what you're going to have. So let me just save it this way. We can simply add this. So we are going to have, this is square root of 5 cos as it is. So I'm just going to take as it is the square root of 5 cos. Okay, sorry for this, guys. Just going to move aside. That's cos 116,565. So we are going to add the real term, which is 3. So add 3. What are you going to have? So this is going to be 2,00 like that. So that's simply a 2 that you're having there. All right, then we move on to the imaginary part, the part where we have got what? A j. That's the part of the imaginary. So meaning to say we are going to simplify this part of the imaginary on its own. This part here, at considering that it is affected by what? A sign, a plus. Affected to the imaginary part of 8, but with the what? A minus. There's a minus there. So you need to consider the sign also that you're given there. A sign. Okay, so let's simplify this. Let's have this first one says the square root. So there's a plus. So plus, guys, we can just write as it is. Square root of 5 sine 116,565. Okay. Okay, just close the bracket of a sign. Then we are going to subtract 8. So that's minus 8, whatever that you're going to have there. So this is minus 6, minus 6, 00 like that. So this is going to give us a minus 6. So that's minus j6. Remember, we are talking of what? We are talking of the imaginary part where we have got a j. So the j is just going to remain as it is. So it will be minus j6, which is exactly the same answer that we got here. But look, simplification, they differ. There, we just had to convert to the normal way that we are used to in terms of the division, convert to the normal way that we are used to in terms of addition, which is supposed to be both in rectangular form. But with our normal mathematics way that we are used, or any way that you want, you can apply the complex conjugate. Applying the complex conjugate is for us to get rid of the j so that it gives us a real term. We have got a real term, which is, remember your complex numbers, guys, from your N4. I cannot explain further than this. So this is going to be up to you in the simplification. Which way do you understand? Which way do you understand? So these are simplifications. You can see now we are now talking of the complex numbers, and this is how we are going to be applying our complex numbers. So know your conversions, your simplifications, which part is easier to work with in terms of your simplifications. Which one are you going to use? The rectangular form for addition and subtraction, polar form, multiplication and division. So with this, you can answer as much questions as you can. So also be part of the membership, like I said, so that in our simplifications, as we are going to be simplifying some other activities, you won't miss out. So just try to calculate as much questions as you can, and we shall talk about this in our membership. Calculate A2 plus J3 into 3 minus J4. Try these questions, then we shall have an explanation in our next class so that you will be able to understand. So like I said, by joining our membership so that you won't miss any of these classes that you shall be given, that we shall be having. There we've got 25 angle of 30 degrees plus 10 angle of minus 5 degrees in a rectangular form. Your answer is supposed to be in a rectangular form for this one. Let it be in rectangular form. And let's also try this one. 5 plus J10 times 2. All right, so let's try as much questions as we can in our simplifications. Then we shall have the revisions in our membership platform.